welcome back to the second part of our demonstration of the new innovations that have been implemented on the ARIS platform. In this section, I will demonstrate to you the transmission diffraction solution that we have introduced together with the parallel plate collimator. And transmission is generally used for lowly absorbing materials to counteract the transparency effect in reflection measurements. And so this is typically performed on organic materials, such as pharmaceuticals, for example. And also today I would like to demo that by two measurements. First, a conventional Bragg-Pentano measurement, and then a transmission diffraction measurement introducing our new sample holders. Let's start with the optical setup first. So again, we have newly introduced new optical component on the diffracted beam path. Before we only had one fixed anti-scatter slit tunnel, but now we have introduced a new design for the fixed anti-scatter slit on the diffracted beam side that allows you to introduce different sizes of anti-scatter slits. We have 9mm, which is conventionally used for the Bragg-Pentano measurements, and for transmission we have introduced 2mm, as you have seen before, and 5mm as well. So on the incident beam side, we have also introduced a new component, which is a combined anti-scatter slit and filter that reduces scattering at lower diffraction angles. So I've already set up the instrument for the measurement, but before I would like to start the measurements, I want to also show you our new sample holders. Those are our dedicated transmission sample holders, which allow you to measure powders that are prepared between foils. In this case, it is a conventional Mylar foil between two frames, and they can introduce into the system like this. And the second type of holders that we've introduced is a capillary sample holder, and this is how it looks like. So basically you can mount the capillary in the center of the sample holder and also measure it in our conventional spinner. The advantage of these type of sample holders is that you can use them in combination with the sample changer, and more importantly, you can even combine them with conventional Bragg-Pentano measurements. And this is what I'm going to demo now. So I have prepared an indomethacin and lactose mixture here in a conventional Bragg-Pentano holder. So this is one of our newly designed low-angle diffraction holders. And I've also prepared it between Mylar foils in our transmission frame holders. And what I'm going to do now is I'm going to start two sequential measurements. First, the Bragg-Pentano measurement that is then immediately followed by the transmission measurement. So in order to protect the samples, I'm just going to mount the cover of our sample changer. And I've pre-prepared two measurement programs. The Bragg-Pentano measurement program is roughly going to take 2 minutes, 20 seconds. And the transmission measurement program is going to take 5.5 to 6 minutes. So, and what I'm going to do now is I'm going to start the first measurement here. So the sample is then picked up by the gripper again, put into the sample loader, and then it is introduced into the instrument. And then, while this measurement is already starting, I can also add the second measurement and put it to the queue. So that means once the first measurement is done, the second measurement will automatically start after the gripper has unloaded the first sample and reloaded the second sample. After the two measurements are done, we're going to compare the raw data again to show the benefit of the transmission application for lowly absorbing samples. And here you can already see how the raw data is built up. You see quite good peak intensities. So now the first measurement is finished. The sample is being loaded out of the system back to the sample position 1, and our transmission sample is now being introduced into the system. And now the transmission data is collected as a pure 2θ scan, similar to grazing incidence measurements. And for that I'm going to switch to the second sample position to see the data being built up again. So now we are transmitting through the sample, which is why this application is called transmission diffraction. So that allows us to prepare very small amounts of sample and very thin samples as well. And by that we can reduce this transparency effect, because generally organic materials are very lowly absorbing. So that means what happens is that during a Bragg-Mentano measurement, again, what we face is we face a continuous increase in sample penetration with higher measurement angles, which means what we will see is we will see a continuous shift in the peak positions at higher angles and also peak broadening. In addition to that, for sample preparation for Bragg-Mentano measurements, we usually also introduce quite a lot of preferred orientation, which is highly reduced in transmission measurements when you prepare the samples between foils, or even better in capillaries. What is important to note here is that I didn't have to change any optics between the two measurements, because I set up both measurements in a way that they can be measured sequentially, which is very convenient because it allows you to combine different types of samples and different types of measurements in the same measurement batch without having to interact with the system. So now also our transmission measurement is done, and we will have a look at the data shortly. Just to be clear, so also the capillary holders, they could be measured in the same sequence, but since the measurement principle is exactly the same as for the foil measurement, I decided not to demo that in that section today, but we will show data in the following webinars, and where we have a much more closer look to data collection and also data analysis. So, but now just I would like to compare the two data sets that we just collected. And again, for that, I open Data Viewer and import the two scans. So, and this is the comparison. And at first sight, the two data sets, they look very similar. So the red one being the transmission measurement, the blue one being the Bragg-Mentano measurement. However, if you look closer, what you do see is that with increasing peak positions, you have an increasing shift in the peak position in the Bragg-Mentano measurement. So this is very clear when you compare the first peak. There the peak shift is quite small, but you can already see that the peak is broader. But then the higher the measurement angle, the larger the peak shift. And this is a result of the sample transparency, which is just a result of the low absorbance of the sample itself, meaning that at higher diffraction angles in the Bragg-Mentano geometry, the beam penetrates the sample to a deeper level, which means that the average measurement, the average sample height in the measurement geometry is getting lower and lower and lower. So this is one of the big benefits. Also in the data, what you see is that the relative peak intensities are different, and that is a result of the preferred orientation that is introduced due to the sample preparation in the Bragg-Mentano sample holder, because we have to press the sample in order to get the flat sample surface. So that means if you compare the two data sets to the relative peak intensities from the databases, what you will see is that the transmission measurement is actually much closer to the expected relative peak intensities from the database than, for example, a Bragg-Mentano measurement. And yeah, hopefully I was able to show you the benefits of the two applications. And that's it from my side. Thank you very much for your attention.